In this video, I'm going to go through the steps of testing the null hypothesis of equal means associated with the exposure effect study, which was relevant to the exposure of faces to people and how much they actually like the look of the person based on the number of times that that particular photo is exposed. And so some faces were exposed only once, twice, 5 times 10, and up to a maximum of 25. And the hypothesis here is that greater exposure leads to greater liking. So this is a within subjects design because each person rated each of the photographs and they were randomized as you read in the textbook. So it's not because one face was more attractive than the other, they actually randomized them across the conditions. So we've got 5 levels here, which means that we can't actually do the protected Fisher's LSD in this case. I'm not going to do that in this video, but I'm just pointing out that we've got 5 levels. It doesn't matter though in terms of just doing the generic repeated measures ANOVA. This is a one-way because there's only one independent variable. There are 5 levels associated with this though, so 1, 2, 3, 4, 5. And we'll just put exposure as the name of that. And we'll add that here. We'll click define, and we'll put these 5 levels into the within subjects variable box. You can ignore between subjects covariates. Click on options. We want descriptives and effect size. In terms of homogeneity tests, there is none, which doesn't apply here. Sphericity does apply, and it'll be outputted automatically by SPSS. I'll come back to doing the post hoc in another video. Plots, we usually want to see the means, although I prefer to see them in the line graph. Click OK. And here we have the exposures 1, 2, 5, 10 to 25. And we can ignore the multivariate test. Moschli's test is sphericity. We can assume sphericity with these data because the p-value is not less than 0.05, it's 0.093. So we've satisfied the assumption of sphericity, which means we can look at sphericity assumed results. So for exposure, which is the only independent variable we have in this analysis, the f-value is 6.85 and the p-value is less than 0.001. So we've rejected the null hypothesis of equal means associated. You know what, I didn't even ask for the means, so I actually got to redo this. Option. Descriptives and effect size, sorry. Should have did that to begin with. So here are the descriptive statistics. The rating starts at 4.36, goes up very tiny amount at second exposure, and for faces with 5 exposures 4.49, 4.44, and then a mean of 4.80. Again, Moschli's test of sphericity is satisfied, and here we have the sphericity assumed result 6.85, p less than 0.001, and a partial eta squared of 0.065. So 6.5% of the variability in liking ratings was accounted for by the number of exposures, excluding the variance that's shared across the levels. In fact, we can look at the correlations as I recommended you do in the previous example with the anxiety study, and we can look at these correlations now. I don't think I reported those in the textbook, but we can see that there are all nice big positive correlations between the exposure levels. And the reason that's happening is an interesting question in its own right, but probably because some people are more easily impressed than others. So when they give a rating to somebody, they'll say, oh yeah, I really like that person. And then they'll get exposed to another face and they'll say, oh yeah, I like that person too. And so, but some people are really hard to impress and they'll say, nah, I don't really like that person. And then you show them another face, and they're like, nah, well, I like that person a little bit more, but I don't really like them that much. So that's what's happening is there's a general liking factor in terms of how people provide ratings. And that is adding to the power of the analysis because that variance is being extricated. So the null hypothesis has been rejected. The means are not all equal. We don't know which ones are unequal to each other. And here is the line graph. We would have to do some post hoc comparisons to follow this up. I'm going to do that in a separate video. And we've got the line chart here. One thing I will point out is you can't get the confidence intervals with this line chart, but you have to go into the graphs line utility here and then put simple and summaries of separate variables, define, put that in here, options, display error bars, continue. I'm just going to paste the syntax for that because I worry one day SPSS will get rid of legacy dialogues and you won't be able to do it through the buttons. But so this is how you would actually get a line graph with the confidence intervals in a fairly easy way. And I'm just going to run this And here are the error bars. It doesn't give you the markers in the middle though, so I'm just going to click on that and show you how I actually got that in the previous example with the anxiety. So you just have to now write add markers, and then you get little circles to start things off. And if you double click on them, then you can get other options. Maybe you want to put a star and make it an 8 size, something like that. Now I did mention, we've already covered the part where these confidence intervals are not accurate. Look how huge they are. It looks like there's nothing statistically significant across any of these. Maybe this one and this, there might be something here, but otherwise it looks terrible. And that's because the correlations across the conditions are not taken into account with these. And so we'd have to calculate the adjusted standard deviations, which is not really that hard to do. I encourage you to consider doing that for all your analyses with the within subjects ANOVA. So this is how I did the ANOVA for this exposure study, but I don't know what's going on for sure. Like I don't know if all these means are different from each other. I have to do the postdocs, and I'll do that in a separate video.